So what we've got here is the contingency paper for 2022. This was just in case anyone came down with COVID for this year. So we're really lucky. We've got two papers for 2022. So I'm going to go through this one. Here's your equations sheet and your prefixes and multipliers. They're going to come into use in this paper. So let's have a look. Question one is a triple question. So triple content only. We've got a mass. We've got a graph showing us momentum going in there. And then it's asking you for 1 mark for the initial momentum, which is 2 kilogram/meter per second. On to the next page then. Again, we're given the equation. So the initial momentum, which we just identified as 2. Over the mass, which I highlighted on the previous page, 0.16 kilograms, which is there, to give me 12.5, another 2 marks there. It says the conversion takes 0.5 milliseconds. So this is where our prefixes come into place. So we can either just put times 10 to the minus 3, or we can actually work that out by dividing by 1,000. I'd advise just to put in the prefix there. So if we just look at this, so the milli is 1 times 10 to the minus 3. So you literally just put that after the number and you can get the mark like that, okay? So we don't have to really convert much in physics. We use that all the time in A-level. We just simply put the multiplier on the end. To calculate resultant force then, so we're looking at change in momentum here, which was 2, because it goes from 2 down to 0, so the difference is 2, and then 0.5 that time, which is there, 0.5 milliseconds, gives us a resultant force of 4,000. And by the way, it's 2 because the momentum's 2 because it's a change in momentum, so it goes from 2 to 0. Okay, and the difference is 2 there. Local conservation then, so this should be one of your definitions, so nice and easy. It's equal to the total momentum, providing no external force. And then you've got this graph at the end for 2 marks. So what we're looking for now is a crossover of momentum. Remember, momentum is conserved, providing no external forces. So what's going to happen is, as this momentum starts coming down, the momentum of the red snooker ball is going to start going up, and then we're going to get to the same amount of momentum. So it's a really, I guess you just mirror the graph that was there before on these things. Let's have a look then down to question 2. So the students decide that there are no anomalies. Explain why. Well, all these readings are quite similar. The range is small. We can say it's repeatable. And then when we're asked to calculate this mean, we're going to use all 3, going to add all 3 up and divide by 3 to give us 0.94. What we're going to do then is we're keeping the mass the same of these cupcake cases, but we're changing the surface area. So this one's got a much smaller surface area than this one. We can see that the speed, the terminal speed there, because this has got a bigger surface area, is going to be a smaller terminal speed, where this one is a bit faster because it's got a smaller surface area. So let's have a look at the questions. Okay, for 3 marks then, we need 3 ticks. So let's go through these. So cake case 2 has the same terminal speed as cake case 1. Well, that's not true because we just got to look and we can see this is 1.6 and this is 2.3. So a little cross in there. Cake case 1 and 2 have identical weights. Well, it's given us a mass. So 0.5, 0.5. That must mean if gravity is a constant, which it is, then the weights must be the same because mass times gravity is going to give me my weight. So that's going to be 50 newtons. This is going to be, 5 newtons, and this is going to be 5 newtons because gravity is 10. A terminal speed, KK, so we've got 3 really similar statements here. So let me go through these and we'll see which one there is right. So terminal speed, cake case 1 experiences a greater value of air resistance than cake case 2. At terminal speed, both cases experience the same air resistance, and then this one's the other way, where cake case 1 experiences a smaller value of air resistance than cake case 2. So what are we looking at here? Well, we're looking at the weight. So remember now, at terminal speed, the forces are balanced. So the arrow going down is going to be equal to the arrow going up. Regardless of the surface area, the weights are the same. We just said they've got identical weights. So the arrow going down is going to be the same size for each of them, which means the arrow going up has got to mean it's the same size for each of them. So at terminal speed, both cases experience the same air resistance because their weights are the same. So you need the same size force counteracting. And then this last statement, at terminal speed, then both cases have a zero acceleration. Yes, that's right, because if you've got no acceleration, then you've got a constant speed. Anytime you haven't got a constant speed, it's either decelerating or accelerating. It's getting faster or slower. But at terminal speed, acceleration is zero. Okay, if the surface area of the cake is halved, the terminal speed will double. Let's have a look if this is correct. So I've said terminal speed for case 1 is 1.6, and when we double it, it becomes 3.2 because we just times that by 2. However, that is not the same as 2.3. So what we're doing is seeing that if we double this, is it the same as that? No, it's not. So the statement is incorrect on that question there. Pushing on to the next bit of the question. So we've got a velocity time graph or a speed time graph here. And you can see it doesn't actually start reading until around about 15 seconds. And that's important. And then we've got the skydiver falling, reaching terminal speed, pulls his parachute, boom, and then reaches a new terminal speed and then probably lands there. 3 marks for 3 correct statements. The skydiver lands on the ground 80 seconds after jumping. From the helicopter, well, let's have a look if this is correct. So 80 seconds is there, which seems to be okay, but it doesn't start until there. So it doesn't start till 15, and 80 minus 15 is not 80 seconds, okay? So that statement is wrong. So that's the time, okay, where he jumps, and that's the time where he lands, and that is not 80 seconds. The terminal speed after the parachute is open is 1/10 of the terminal speed before. So let's have a look. So the speed before was 50. The speed after is 5, and that is 1/10. So that's correct. The skydiver's weight is greatest. Well, we just talked about this, didn't we? The skydiver's weight is going to be constant throughout. It's not going to change. It's going to be all the same. So that's incorrect. The parachute is open 30 seconds after the skydiver leaves the helicopter. Let's have a look. So the parachute is opened around about 45 seconds. How do I know that? Because the speed dramatically decreases. And that's where he jumped out. So 45 minus the 15, 45 minus the 15 gives me 30 seconds. So that is correct. And then these last two, at point B, the weight of the skydiver is greater than the air resistance. Well, again, we're going to be, look, at point B, the weight is, because this is slowing down now, the arrow going up has got to be much bigger. So the weight is going to be constant throughout, but the arrow going up is going to be greater to slow him down. So that is incorrect. And then at point A, the skydiver stops accelerating. Let's have a look at point A. Yes, because we're at terminal speed. Okay, so a long question there. A lot of time spent on that one, but there are some really good marks there. Come to a triple question now, which is all about moments. So what we've got is a practical where we try and balance this ruler by applying weights, different weights at each distance, so different distances on the ruler to try and get it to balance. So we can see we've got a bunch of data there. As we move weight 1, which is 4 newtons, it balances at all these when weight 2, 10 newtons, is at these points. So that's when the ruler balances. And there are equations out there that you can balance the law of moments, where you can see where that point of balance is when every one of these is equal. So we need to keep that in mind there. Okay. So Mary states the resolution of the ruler is 1 centimeter. Is this correct? Yes, it is, because the ruler can go up by a division of 1 centimeter each time. So that's going to be the resolution. So it's adding or taking the minimum you can from that measuring device that you're using. Come to the graph then. So this is worth 3 marks. I'm literally plotting D2 And remember, it always goes up. I've seen some which start at 16 and go up to 4. So be careful of that. We're always going to use equal amounts. Equal amounts on the bottom for distance 1. So your results from distance 1 you would get from there. And your results from distance 2 you get from there. And that's why it's important to go up from the smallest value, because it's got 0, 0 there. So that should be 3 marks. Don't use a pen, because you can see I've made a mistake on some of these bits there. Now we're going to have some questions on this. So this one's quite a tough question, but it's quite achievable at the same time, because it says use data from the graph. Now if they'd said use the gradient of the graph, you'd know straight away that the gradient, hopefully, is the change in y over the change in x. So we're going to take value from the y side and the value from the x side. Well, I've just gone with the maximum values here, so 16 and 40. So 16 change in y over the change in x, which is 40. That's going to give me 0.4. And then it tells me the equation I can use. So I'm going to use weight 1 and weight 2. So weight 1 is 4, weight 2 is 10, and that gives me 0.4. So that is correct. Where do I get the weights from? They're back on this table. So there's weight 1, all 4s. Weight 2 is 10 newtons there. So, the question itself is quite awkward to read, but the maths involved is quite simple. Mary now places the 10 Newton weight at a distance of 32. So she's taken this heavy weight and she's taken it at 32 centimeters from the pivot. Use the equation to calculate the moment. Now, this is kind of like step 1 when we're balancing these. So we're just going to use the moment equals force times distance. To go, so force of 10 times 32. So this was a step 1. And then usually our step 2 then would be to find something on the other side if we was doing it for that conservation of momentum, where clockwise equals anti-clockwise. A little bit different this time. We're given the moment. Okay, we just worked out that moment, and now we need to find that distance, because they say explain using moments why the ruler cannot now be balanced. Now, let's do the distance first. Let's work out the distance. That's my moment over my force, which is 4 newtons, because weight is a force. And I come out with 80 centimeters. Now, 80 centimeters is too long for this ruler, because the ruler itself is only 1 meter long, which means I've got 50 centimeters there. So 80 centimeters would be all the way from, so 80 centimeters from the pivot, the ruler would have to be this long, and it's not long enough. So that's why we're saying it's not long enough. So so we can't do it, okay? I was looking for a statement then, but there is no statement. Question 4 then, a fitness app. We can see that we've got the number of weeks for April and June. We're told that the total was 610, so 610 kilometers for June. Let's work out April. So we need to add this one, this one, this one, and this one together. So we see 190 plus 190 plus 290 plus 240. So it's reading scale gives me 910 kilometers. Let's move on to the next page. Okay, so we're going to have to do a bit of speed, distance, time here. So we got 31 hours, which is a time. We got 19.25 hours for April. That one was for, so this one, sorry, is for April. This one's for June. I know my distances from the previous page. So I'm just going to find my speed, my average speed for both of these by using speed equals distance over time. This you'll find in the front of your formula book. So we come out with 28.9 and 31.7. So the statement is correct, because they say they say that the mean speed of the cyclist is greater in June. And you can see that it is 31.7 there. Just in case you didn't know, so my time from there, and then my distances from this page that we just worked out by here, okay? From June and April. On to a triple question then, which is the SUVAT. They've given you the equation. I've written down what I know anyway, just in case they didn't give me the equation. I know that they haven't given me a V, so I'm not going to be looking for a formula with V. I'm asked to find A, acceleration, so I'm going to use this one. This is the only formula that doesn't have V. So then I just plug in. It's really important you don't try and rearrange this equation, to solve for A before, because you can get marks for just putting 42 in, 42 meters there, which is my S or my X value by here, my displacement. My initial velocity is 8 meters per second. My time is 3 seconds, 3 seconds there, and then half 80. So once you put all that in, then start to simplify, simplify again until you come down to this bit by here. So 3 marks for getting at the answer of 4, and then another mark for saying acceleration is measured in meters per second squared. A quick formula then from page 2. Mass of the cyclist. Well, I've got an acceleration, I just worked out. I was given a force. Was I given a force? Yes, I'm given a force in red, 284. And then it's just a quick rearrange, 71 kilograms. Last bit of the question, which is probably the easiest bit of the question, because we're told that that is the mass of the cyclist and the bike, right there. And now we just want the mass of the bike, so I simply subtract the mass of the cyclist from the mass of the bike and the cyclist. Okay, next one. This is a Hertzsprung-Russell diagram, and we're told that the sun is going to go into a red giant. The sun will eventually turn into a red giant and then into a white dwarf. And it says that the arrow shows the path that it'll take as it turns into a white dwarf. And we need to then tell the examiner about what's going to happen with the temperature. Well, the temperature is higher at this end than this end. So at first it starts to increase and then it's going to decrease. And that you'll get 2 marks from that. And then what happens to the brightness? Well, it's going to decrease because there's the brightness on the side, or luminosity. This is sometimes labeled as, and we can see that gets higher. So as it comes down, it's lower. So it decreases in its luminosity, it gets dimmer. This is all from core knowledge then. So it goes from a main sequence to a supergiant to a supernova, from a supernova then either to a black hole or neutron star for 3 marks. And then we're given some space distances. We're told that it is 8.6 light years away, and then we're told that 1 light year is 63,241 astronomical units, and 1 astronomical unit is 1.5 times 10 to the 8 kilometers, and we want it in meters there. So I'm wondering, I might have done this incorrect actually, because that will stay in kilometers. Let me just pause the video just to check myself. So I'm just looking at the mark scheme now. Yeah, I've forgotten to do a step here. So what I'm doing is, I've taken the 8.6 and times that by the number of units in an AU. So we get that many AUs. If we know 1 AU is worth this, so one of those, I need to times 1 AU by what I just figured out there. That's going to give me an answer. And then I will need to multiply that then by 1,000 to get it into meters, because there's 1,000 meters in a kilometer. Okay, and that's not shown there. So that's a step I've missed. But that's quite a tricky little question there for 3 marks then, because you've got to do that conversion at the end. Okay, coming to the end of the paper now. So this is a triple question. So we've got core knowledge here, state 2 conditions needed for fusion. So very high temperatures, very high pressures. That should be a nice easy 2 marks. Then we've got to draw on here the wavelength of 590 times 10 to the minus 9. And again, this is now knowing that a nanometer is times 10 to the minus 9. This will put a lot of people off. But if we just, and it's worth doing this, let me just show you up here that a nanometer is times 10 to the minus 9. So it's just getting used to these little things. So let's go back to where we were. So I'm just looking for 590 here. You can see the scale is 590 right by there. And then describe and explain how the position of A would be different if the star was distant galaxy. So I said a longer wavelength. So it's going to be shifted to the red end, red shifted, moved to the right, since that is moving away from us, and that wavelength is going to be stretched. It's just called red shift. Question 7, another triple one. This is on fission. Now, sometimes they will try and catch up, because this is not in the spec, a fast breeder nuclear reactor. We're always told that we're always taught that neutrons need to be slow, but in this case, we can have high-speed neutrons splitting the nucleus of barium here. Anyway, let's answer the first question first. So, first stage, I get uranium. Second stage, I get 1 electron there. Third stage, I get an electron there. So, state the total number of beta particles. Well, this is knowing that a beta particle is a fast-moving electron, so I'm going to get 2, because I got 2 there. Then we're given that equation. Explain the purpose of a moderator. It's to slow down fast-moving neutrons to be captured by the nucleus. And then suggest why a fast breeder nuclear doesn't require a moderator, because it happens with fast neutrons, so no need to slow them down. So a little bit of information there from the text. The advantages and disadvantage then of storing waste in a certain way. So I'm assuming that you've read the questions in these just to save time on the video. So the advantage is there's going to be a large distance between the place of storage and people, because it's deep underground. The radiation can also be absorbed by the earth, just in case there is a leakage, so it reduces exposure. The glass or the concrete is stable for thousands of years, reducing the risk of leaking. There's employment. There's, it's easy to monitor in this long-term storage. However, we need to put it in a place that's geologically stable, so which means no earthquakes. It's going to be really super expensive to build and monitor. This waste has long half-lives, so that's going to be thousands of years. So, almost more than 10 generations of workers just watching this waste and monitoring this waste. And then safety and security risks, so anything with transport there. So a bit of a common sense question. It's a nice 6-mark question. I say out of every 6 marks, we should be pulling 3 marks. And I think 3 marks are achievable there. Okay, question 8. We're almost there. I think this is the last question. Yeah, I think it's 3 pages. Question 8. We've got this data leaflet and it shows us this. And then we've got a spring that's unstretched. A spring that's unstretched already starting at 4.5. So that, again, there's a lot of scale reading in this paper. And then we've got a spring that's stretched with a certain weight on, which is 10.5. Let's have a look what the question is going to ask us. Use the information then. 2 pictures determine the extension. So that's going to be the difference between unstretched and stretched. So that's going to be 6 centimeters. Then we're told that G is worth 10 newtons per kilogram. And we've got the weight, which is the force. And we've got gravity to work out our mass. So the weight I've got from the graph. So let's have a look. We just worked out we got an extension of 6. And that gives me a weight of 3. Okay? So my weight is 3 over 10. That gives me a mass of 0.3 kilograms. Oh, what a lovely question. State Newton's third law. That's all core knowledge. And then it's a third law pair now. So what we're saying is, a third law pair is if the spring and the mass are both different, so object A and object B, then state the size and the direction. So the size of the force that the spring has to apply has got to be 4, because 4 is being applied to the spring applies 4 back. So it's equal and opposite. So because the weight is pulling down, the spring is going to be pulling up, and that's the opposite bit there, okay? And then the last page, last question. We've got this equation in the front of our books, work equals half Fx, which is pretty much the area under the graph here. So there's my force, there's my x, my extension, and it's going to be the area. That's why it's half, because it's that triangle. Remember, Hooke's law is proportional, and then when it starts to bend, that's the elastic limit. Just a reminder there. Anyway, for 2 marks, what a lovely question. So we're given a force, 35 newtons. We're given an extension, 0.32 meters. Don't forget the half, 0.5, 5.6 joules. And the very last question, we've got to use this equation again now, down here, okay, to work out if it is directly proportional to extension. So I'm going to, if it's doubled, so I'm going to redo my force. I'm going to double my force. I'm going to double my extension from 0.32 to 0.64. So I'm just using all of this, just doubling it. And then I'm going to plug it back into this formula to see how many joules I get. 22.4, and that is not double 5.6. All right. So hopefully you've got something from this paper. And if you do have any questions, please come and see me.